So today in class we learned about resonance in strings. As you know, this happens when we have forced vibration at an object's natural frequency. Here we're learning about what happens when you have resonance on musical instruments, string instruments as well as wind instruments. Starting off with those string instruments, things like a guitar or a cello or a violin, you'll see as it says here that all points on that string oscillate together vertically with the same frequency, but some points have different amplitudes than others. Basically, we create a standing wave on the string itself. As you can see in the diagram that's listed here, which is taken from your textbook, we have a length of a string, as is shown here, and then we have that simplest standing wave right here, where you get nodes on the two ends and antinodes right smack dab in the middle there. As you can see on this diagram here, the length of my string is equal to half of a wavelength here. If I needed to complete that full wavelength, it would look like this, and then it would go down again and come back up. That's important. We'll come back to that later. The next one comes up here where we have a node in the middle all of a sudden and nodes on both ends. So I have three nodes and two antinodes, as you'll see here. This time I have a full wave on my string, so the length of the string is equal to one full wavelength. On the next portion down here, I have the next standing wave, and you'll see that I now have four nodes and three antinodes. As it shows here, I have 3/2 of a wavelength on the length of my string. These things have special names. They're called harmonics. So this picture over here, we call the first harmonic. And you'll see that I have an n equals 1 on this picture. For this second one over here, this is called the second harmonic. And an n equals 2, and then the n equals 3 for my third harmonic. We're going to make use of this relationship between the length of my string and the wavelength as we go through and create an equation here. So I know from the last chapter that the speed of a wave is equal to its frequency times the wavelength, which means that frequency is the speed of the wave divided by its wavelength. The speed of the wave on a string is something that would be given to you because it's how a wave travels through a solid. And looking up at my picture up here, I have different relationships for wavelength in each of these. If I were to solve each of these for wavelength, in this first harmonic, I'd have that the wavelength is equal to 2L. The second harmonic, the wavelength equals L. In the third harmonic, the wavelength equals 2L over 3. I'm then going to plug those in to my equation for frequency here. I'll put a little 1 down there for the first harmonic, and so I get V over 2L. For the second harmonic, it is just V over L. For the third harmonic, it is 3V over 2L. I just flipped that fraction there. You might not see a pattern quite yet because it's hard to tell with this second one right here. It doesn't seem to follow the same pattern. But if I multiply this by 2 over 2, it may be more clear that there's a pattern. Take some time right now to figure out what you think the pattern is. Just pause the video. Did you come up with a pattern? Hopefully you found a pattern that looks something like this. The frequency of the nth harmonic, we can plug in any number there, is equal to N times V over 2L. Each of these has a 2L in the denominator. Each of them has a V in the numerator. And you'll notice that when I have F1, I have a 1 here. When I have F2, I have a 2 here. And in F3, I have a 3 here. So that letter N in this equation is any positive integer. We can have as many as we want. So that's harmonics on strings. We also have harmonics in pipes. So when we have resonance in pipes, there are two types of pipes that we'll talk about. They're called open and closed. The thing that makes them different is that an open pipe has two open ends, and a closed pipe only has one open end. The other end is closed off. We'll look at the open pipes first. One thing you'll notice is at the open end, the very edge here, we have an antinode. A fact about resonance in pipes is there is always an antinode at an open end. This other end here happens to also be open, even if in this picture it doesn't quite look like it is. So we have two open ends, we have antinodes at each end. The simplest way to get a standing wave is to have a node in the middle and the two antinodes on each end. It's important to have antinodes on any open end because the sound waves need to escape your instrument. They need to escape your pipe. So looking over here, this tells us a little bit about those waves. I'm going to start by looking at this first picture here. And to make it easier to see, I'm going to just trace one of these waves here. Hopefully it's clear to you that this is half of a wave. I'd have to come back up to the other side for it to be a full one. So for this first picture, this first harmonic in this case, the length is equal to half of the wavelength. On the second one, as I trace that one, I have one whole wavelength. I go peak to peak. So the length is equal to the wavelength. Finally, in this one, I go down and back up. There's one full wavelength, and then I have another half. So in this case, the length of my pipe is equal to 1.5 or 3 halves of a wavelength. You'll see that on each of these, except for at this time, they solved for wavelength. So wavelength equals 2L for the first one, wavelength equals L for the second one, and wavelength equals 2/3 L for the third one. Then we go ahead and put it into the equation, just as we did in the last section when we were talking about resonance on strings. When I put 2L into my equation for the first harmonic, I get V over 2L. For the second harmonic, I just get V over L, but again, I could put a 2 in the numerator and in the denominator. For the third equation, I get 3V over 2L. It follows the same pattern as the previous one. Therefore, it has the same equation. The frequency of the nth harmonic equals NV over 2L. And again, N can be any positive integer. Closed pipes are a little different. So let's look at those next. A closed pipe, as I said, means that there is one end that's closed off. And you'll see that that's true. This time this end is closed off. And you'll notice that there is always a node at a closed end. That always has to be the case. The simplest way to get a node at a closed end and an antinode at an open end gives you this form of a wave. And this happens to only be 1/4 of a wave. So the length equals 1/4 of the wavelength. In the next one, I'm not quite there at a full one. I would need to do that to be at a full one. So this time, my length is 3/4 of a wave. In the final one, I have more than a full wave, because that gets me to a full wave right there, but I have that little bit extra. This time, the length is equal to 5/4 of a wavelength. Again, looking at the equations that are written here, the wavelength equals 4L for the first harmonic. The wavelength equals 4/3 L. This one we call the third harmonic. And the wavelength equals 4/5 L. We call that the fifth harmonic. Now you might notice something odd. Where's the second and fourth harmonics? With closed pipes, pipes that are closed on one end, we only have odd harmonics. It's a little bit different here. And we have a different equation. Go ahead and take a minute right now to try and figure out how the equation is different in this portion. Maybe you ended up with the following equation. The frequency of the nth harmonic equals NV over 4L this time. And n is special because now n can't just be any integer, but n has to be an odd integer. 1, 3, 5, 7, 9, so on and so forth. That's what makes these two types of instruments different. When you have an open instrument, you have NV over 2L. N can be any integer. When you have a closed pipe, NV over 4L, N can be only odd integers. A quick comment before we move on to one example problem is that the first harmonic has other names. Sometimes the first harmonic is called the fundamental frequency, and sometimes the first harmonic may also be called the natural frequency. So you may see any of those terms referring to that same concept. Moving on to our example problem. This is talking about a guitar string. So we have a standing wave on a string, or resonance on strings. Has a frequency of 540 hertz as its third harmonic. It wants to know its fundamental frequency if it is fingered at a length of only 60% of its original length. I want to see if you can figure this out on your own. Go ahead and try this one. When you are finished, check the second video to see how you did.